You just realized your business needed to hire someone yesterday. How can you find amazing candidates fast? Easy. Just use Indeed. Stop struggling to get your job post seen on other job sites. With Indeed sponsored jobs, your post jumps to the top of the page for your relevant candidates, so you can reach the people you want faster. According to Indeed data, sponsored jobs posted directly on Indeed have 45% more applications than non-sponsored jobs. Don't wait any longer. Speed up your hiring right now with Indeed. And listeners of this show will get a $75 sponsored job credit to get your jobs more visibility at Indeed.com/PODKATZ12. Just go to Indeed.com/PODKATZ12 right now and support our show by saying you heard about Indeed on this podcast. Terms and conditions apply. Hiring? Indeed is all you need.
Time to take a short break to tell you about our sponsor NordVPN, and they've got a great New Year deal for you, which I'll get to soon. Now, if you're someone who uses public Wi-Fi, then you could be exposed to hackers, and I'm talking about places like cafes, airports, hotels, shopping malls, anywhere that Wi-Fi exists for open use, basically, and let's be realistic, there aren't many places that don't offer it these days. Now, you might not be aware of this, but there are two ways hackers work. They can hack into your device directly, or they can intercept your Wi-Fi data, which could include your passwords and usernames. And once they get that, all bets are off. So what can you do to ensure your safety? Simple. Put up a wall known as a virtual private network, or VPN. This is software that makes you untraceable and therefore unhackable, and there's none better than NordVPN. As a Space Nuts listener, we have a special New Year offer available to you. Just go to nordvpn.com/spacenuts. That's nordvpn.com/spacenuts and click on Get the Deal and check out what's on offer through their monthly, yearly or 2-year plans. And the longer you sign up, the lower the overall price, plus an extra 4 months free, and of course, their 30-day money-back guarantee. And don't forget all their other amazing tools like cloud storage, threat protection, anti-malware. My favourite is the password manager, makes life so much easier. All available depending on which plan you choose. It's inexpensive, simple to set up, and you can use it on 10 devices through most operating systems, which is very impressive. Check it out today at nordvpn.com/spacenuts. That's nordvpn.com/spacenuts and click on Get the Deal. You won't be disappointed. Hi there, thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. Great to have your company. Coming up on this episode, we are going to look at Earth's core. And it's sort of hit the news lately, but this is not a news story, but we thought we'd better talk about it just in case you're wondering. Earth's core is slowing down or not doing what you'd think it would normally do. So we'll talk about that. There's a hyperactive star out there and it's got a planet. What does that mean? It means it's pretty darn quick. We're going to talk space dandruff. Yes, it's true. And a new planet that's sparking a bit of debate on its status. If we've got time, we'll do that one. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
He's back for more. Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Hi, Jonti.
Hey, how are you going?
I am well. How are you?
I'm getting there. I'm not a morning person. As I was saying, I got woken up earlier than I was planning this morning by a phone call that said, can you go on live on the radio in 5 minutes? So I got to be a zombie on live radio, which still was good fun.
Those pesky journalists, yeah.
Groggy ever since. Yeah, I have great sympathy for anybody who works a morning show. I think we were talking about this last week. Yeah. But it must be hard. But I'm not at my best at 20 to 7 in the morning. This is a more reasonable time, but this is still morning. It's 20 to 12 at the minute. I used to work with the people conscious.
I used to work with a journalist who used to have to do the police rounds first thing in the morning to get any news from around the various police districts, car crashes, all that horrible stuff. fires, etc. And after a council meeting, they used to have to ring the mayor at Sparrows in the morning. We had one particular mayor who was always nearly asleep when they called, and they could never get a good quote from him because he was just non-compos mentis.
Not much time of the day.
It was a frustration for the journalist, I can tell you.
If I'm going to do something at 5 a.m., I'd rather have stayed up all night to do it than set my alarm early.
Yes. Well, I never had a choice for 30-odd years. But anyway, that was my choice, even though I didn't have a choice.
And now you have your freedom. So that
I do. Now, let's get down to business. Earth's core, the rotation thereof. This is a story that's been around a little while, but it keeps popping up. It popped up again on the weekend, and I thought, well, let's talk about it. We may have talked about it with Fred. I got an inkling that when it first came up, we went there. But yes, it's something that the press is certainly honing in on.
Yeah. Well, there's a few little factoids about this that really caught my eye, actually, when you sent me the link through, because I managed to miss this one. These are researchers at the University of Southern California, so USC, and they've been looking at earthquake data. So if we want to study the interior of the Earth, with the best will in the world, we can't drill down there. You know, the deepest hole ever drilled was less than 10 kilometers, I believe. And the Earth is frustratingly opaque. We can't see the interior because the ground's in the way. So we've learned everything that we know about the interior structure of the Earth, the core, the mantle, how they all behave through earthquakes. So you get an earthquake and seismic waves travel outwards in all directions. There are two different types of seismic waves in a very rough sense. And when they go from one medium to another, their speed changes and they refract in just the same way light does when it enters a swimming pool. Same kind of idea. So if you're measuring these earthquakes using seismographs from all around the world, you can back out what the interior of the Earth looks like and its properties by the time it takes the different types of seismic waves to reach you, essentially. And by doing that over an incredible long time, we've got a very detailed picture of the Earth's interior, even down to, the temperatures, the pressures, the compositions. And people are monitoring this all the time, but the finer the detail you want, the more challenging it is to disentangle the information about the earthquake itself from the information you're learning about the interior. And this is something we see a lot with finding exoplanets. There's a perverse analogy here that we're looking at the light from stars, and to get a really good idea of what the planet's like, you've got to understand the star first, because that is overlaid on the data and you've got to disentangle them. So to get a real handle on the fine details of what's going on in terms of the Earth, your ideal situation will be to have every earthquake be identical to the last, so that all the earthquakes were the same and you could take that out of your analysis. You could essentially account for that. And that was the first thing I saw in this article that I thought was really interesting. I mean, obviously the results are cool, but it's the way they got them. They looked at this sample of what are described as repeating earthquakes. They got data from these earthquakes near the South Sandwich Islands, 121 of these that occurred between 1991 and 2023. And it says repeating earthquakes are seismic events that occur at the same location and produce identical seismograms. So rather than using all the earthquakes from all around the world, they use this one subset that gave them very controlled data. And that lets you get very fine resolution on the things you're looking at, because you're not adding extra noise, essentially. And by doing all this, they learned a couple of new things about the Earth's inner core. So we've known for a while that while the Earth has a core, the core actually has two layers. It's got a molten outer core, which the iron and the nickel are essentially liquid. They're moving. Well, they're molten. So they're a fluid. They move around. And that movement is tied to the formation of the Earth's magnetic field. You get the induced magnetism that gives us a magnetic field. Interior to that, where the pressure is high, even though the temperature is so high, the pressure is such that the inner core has been thought to be solid. And so you've got a solid with a liquid layer outside, and then the molten layer of the mantle, then the solid layer of the crust, as a rough kind of structure. What these new results have shown us, the headline act is that inner core doesn't spin perfectly constantly. It had, apparently for a long period of time, which I wasn't aware of, people were aware that the spin speed of that inner core was gradually increasing. It was speeding up a little bit, almost imperceptibly. But what this research has shown is that more recently, it has now started to slow down again. So that's a headline act. The inner core has slowed down a little bit. And they're talking about here at a scale of about 1,000th of a second for the rotation period. So it's a tiny effect. but they can measure it thanks to these repeating earthquakes that have the same signature that allows them to get a much better resolution on the data. The other thing which I think is very interesting that isn't in the main press release but is in a couple of the other articles is that these same data suggests that the inner core is not totally solid but actually has molten areas within it. So this is a bit of a change to the paradigm we had of this very simple model of a solid inner core, then a molten outer core, that there's actually a bit of moltenness to the inner core as well, which probably makes a bit of sense in the context of this thing's rotation changing over time. If you've got bits that are melting, bits that are moving around a little bit, you're moving angular momentum around, so therefore you'll change the rotation period. In just the same way that the rotation period of the Earth as a whole will change if the ice caps melt. Will change in a measurable way because you're moving mass from the poles to the equator. Redistributing that mass will mean that the Earth's spin will slow a little bit to conserve angular momentum. So it's a fascinating story, and I think, yes, the headline side of it, the inner core has slowed down. That's interesting. That's the headline story. But to me, the really interesting stuff was how they figured that out, and the subtleties of the choice of earthquakes to use, and the additional things they can figure out. It really shows the benefit of continuing to get longer data sets and reanalyzing what you thought you knew when you've got better data and better instruments. So it's a very cool story, and I do encourage people to have a look around. There's a few different versions of the story out there on the web. Even CNN covered it at one point. So it's got a lot of interest, and by reading a variety of stories, you can get some of the different cool facts that maybe the main press release didn't pick up on.
Yeah, they figured this out by studying, 121 earthquakes between 1991 and 2024.
Yes.
How accurate do you perceive their data to be?
Well, I trust them. At the end of the day, it's peer-reviewed and published, so there's a certain confidence of fidelity there. That's good. And I find their data selection really interesting there. The fact that you've got thousands of earthquakes happening all the time. You know, we see what's happening in Santorini at the minute with what is probably a very large motion of magma underneath that ancient volcano that suggests it may well erupt again at some point soon. Similarly, under Naples. So earthquakes are happening all the time, all around the world. And what I loved about this was finding this subset of earthquakes that are happening recurrently at the same place that are giving them the same signal, which makes the data analysis much, much, much better. I just really like that. And it's why, in exactly the same way that we can find planets using our radial velocity, the wobble method, much more easily around quiet stars than active stars. Because active stars are roiling and bubbling and boiling, so the lines of the spectrum of the star are moving around because of the properties of the star that introduces a lot of noise. When you've got a quiet star, a star that isn't very active, a bit like the sun is, that noise is much less, which means that you can resolve much smaller motions thanks to the planets. And so you can detect smaller planets around stars that are less active. And it's a direct parallel here. By getting a much simpler set of earthquakes that all behave the same way, you reduce the noise and therefore you can get a much more accurate impression of what's going on in the interior. So I guess if you want to look at timescale changes in the mantle and stuff like that, you can use all the data set and map it that way. But for something like this where you need that really fine-tooth comb, it's a beautiful way of doing it.
Yeah, it's a fascinating story. It's we're so close to it compared to everything else we study in the cosmos, but it's it's invisible to us. We have to dig deep. Boom, boom.
Techniques that are getting developed from this that then apply in astronomy and in planetary science. You know, we talked previously about InSight, which sat on Mars and recorded Mars quakes, and that was just single station. I would love at some point in the future, perhaps when Sir Elon decides that he's finally going to move to Mars, if he could take some seismometers with him and drop them in a variety of positions, that'll give us a lot more information on Mars's interior. Similarly, these kind of techniques are very similar to what my colleagues at the University of Southern Queensland and elsewhere around the sphere of academia use to study the interiors of stars. Because you've got the same problem. You look at the sun, and it's our nearest star, but all we see is the surface. You can't see inside it because the surface is in the way.
Yeah.
How do we know about the structure in the interior? It's exactly the same kind of thing they're doing here, but using star quakes and star wobbles rather than earthquakes.
Yeah, really interesting stuff. And if you'd like to read more about the inner core of our own planet slowing down, just do a search for that. It's everywhere. You can find it on Discover magazine and a few other sites. Let's take a little break from the show to tell you about our sponsor, NordVPN. Now, I've been using NordVPN for almost 2 years, and without a word of a lie, I have been very impressed, not only with their VPN, but all their other products. I've used VPN overseas, yes, but also I use it in my day-to-day activities. I've set it up on my smartphone, and it's always on, and it keeps me protected 24 hours a day. And no, I do not notice any difference in the performance of my phone when browsing the internet on Wi-Fi or mobile or cell towers. It's seamless, it's simple to use, and you can load it onto 10 devices, including your smart TV, your tablet, your PC, your MacBook, whatever. As a Space Nuts listener, Nord has a special birthday offer with big savings for you, and I'll give you that URL shortly so you can take advantage. First of all, there's an extra 4 months available for free if you sign on for their 2-year plan. But right now, they're offering a Nord coupon as a part of the deal, which offers 6 months of NordVPN that you can use yourself or share with someone else. You can check out all their deals and services at nordvpn.com/spacenuts for their exclusive deal for Space Nuts listeners. That's nordvpn.com/spacenuts, and they back their gear. They have a 30-day money-back guarantee. Don't forget about that. nordvpn.com/spacenuts. Check it out today. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, let's go to this story that is talking about a star that's been described as hyperactive. This is a star that's moving, well, it's probably one of the fastest, if not the fastest, ever discovered. This story is quite amazing.
Yeah. So this is what's called a hypervelocity star, and we do know a few of these in the Milky Way. These are stars that are traveling at such a high speed that they're traveling faster than the local escape velocity for the galaxy at their location. So we're on the surface of the Earth, and if I throw a tennis ball up in the air, it will fall back down. I'll catch it or I'll fail to catch it because I'm English and the English cricket team's doing terribly at the minute, so I'll probably fail to catch it because that's where I'm from originally. If I threw it hard enough, the Earth's gravity wouldn't be able to hold onto it and it would escape. And for the Earth, that's about 11 kilometers a second. The more massive you are, the higher that velocity is, but the further you are from the mass, the lower that velocity is. I mean, it's the kind of thing we teach in first-year astrophysics as an equation for the escape velocity, where you can work it out, and I think it's a square root of 2gm over r. Now, what beyond that sounds about right. So that's basically, it's related to the mass of the thing you're going round, and it's inversely proportional to the distance you are away from that thing, with a square root there. What that means is that anything that has mass has an escape velocity. So technically, I have an escape velocity. If you put me in the vacuum of space, far away from any star, and gave me that tennis ball, I could, in theory, nudge it gently and make it orbit me, but if I nudged too hard, it would escape. But even though I'm far too heavy, my gravitational pull is incredibly weak because I'm only 130 kilos, not the mass of the Earth. What that means from the point of view of our galaxy is that our galaxy has an escape velocity that varies depending on where you are in the galaxy. Nearer you are to the middle, the higher the speed you need to be traveling is to escape. Just as in the solar system, it's harder to escape from the sun when you're near Mercury's orbit than it is when you're near Neptune's orbit. So that's how stars move. And a small fraction of the stars in our galaxy, because they're constantly moving around all the other stars, because there's things going on, a small number of those stars will eventually get ejected from the galaxy entirely. Now, quite a few of these, actually, that are previously known are linked to stars that were in a binary star system that was quite close, and then one of the components went supernova, and suddenly it's like the lead was cut, so suddenly they're ejected at very high speed.
Right.
But that's not the only way you can form them. Hypervelocity stars then are these stars whose speed is so high that they will probably escape and never return, that will wander the void between the galaxies in a very lonely life forevermore. The other side of this story is planet detection. We've talked before about how the two most successful methods for finding planets are the transit method and the radial velocity method, essentially seeing stars wobble and wink. There is a technique called gravitational microlensing that if you went back to the late 90s, people were really hoping it would find gazillions of planets, that it would be really successful. And it's never quite found as many as people expected because it's fundamentally hard to do. It's not that these events aren't happening, it's just that they're very hard to observe. But going back to 2011, a team of scientists that were looking towards the galactic core, where you've got the most stars on the sky in the smallest area, observed a gravitational microlensing event. They saw a background star brighten and then fade away again, but it had a double peak in the brightness. So there were two peaks as it went up, and then it went up further, and then it fell away again. And that was indicating that in the foreground between us and that star, something had passed in front that had mass. That mass, curving space-time, acted as a lens, bent a little bit more of the light from the background star towards us, and that's why we saw the star brighten. And then as the thing in the foreground moved away again, the lens went away and it faded away again. And when these events happen, you could infer quite a lot from studying the degree to which the thing brightened and faded, and also the timescale over which it happened. And the team at the time announced their results. This is really exciting, but there's a little bit of what we call a degeneracy. There are two different models that can equally well explain what we've observed. The first is that you've got a star that's about a fifth of the mass of the sun, with a planet that is about 29 times the mass of the Earth. That's scenario one. So you've got a star with a planet. The other scenario is that you had a planet the mass of Jupiter with a tiny little moon. And in either case, the ratio of the mass between the big thing and the little thing is about 2,300 times. Either of these scenarios could explain perfectly well what was seen. So how do we differentiate between them? Well, one thing we can do now that we've got better telescopes and better technology is to use the Keck telescopes, which are among the biggest in the world. They're incredible instruments in South America. And also the Gaia spacecraft, which it's just finished its mission, but it spent 12 years in orbit mapping the positions and the motions of up to 2 billion stars with unprecedented mind-boggling accuracy. So the team that found this object in 2011 saw this signal in the gravitational microlensing, said, one way that we could distinguish between those two different models is to look for the thing that caused the lensing. If it's a star, in theory, there'll be a point of light there that's moving that we can see, that we can track back and say it was in the right place at the right time. We'll be able to see it, and that shows that the thing that did the lensing was a star, so it's a star and a planet. If we see nothing, then the star doesn't work, because if there was a star there, we'd see it, so it must be the other scenario. So they went away and dug through that data, and it took them a bit longer than expected, but they finally found a star that is moving ridiculously quickly, but was in exactly the right place at the right time to cause the microlensing event. And that star is also quite near the middle of the galaxy, so it was quite far from us, quite near the thing it was lensing at the time. They've tracked it back, and it turns out that the movement of this star just at right angles to our line of sight, so the movement across the sky, gives it a speed that is almost 2 million kilometers per hour. 540 kilometers per second.
Blimey.
That is ridiculous. You know, stars nearby, near the sun that are moving around, we typically talk of speeds of tens of kilometers a second, maybe a bit more than 100. So 540 is ridiculously extreme and is already almost the escape velocity of the galaxy at that point. Now, the unknown here is that there could be some movement towards or away from us as well. So we only see the movement on the sky. And essentially any movement that is radial towards or away from us will be enough to mean that this thing is unbound by the galaxy, that it will eventually escape. It is therefore a hypervelocity star, and this is the very first time a planet has been confirmed around a hypervelocity star. Now, planets will form around these stars, that's fine, but to get the very first one, that's kind of cool. And that's a planet that is significantly more massive than the Earth. That star probably has other planets. Where you find one planet, there will be more. So this is a planetary system that is on a one-way ticket out of our galaxy, never to return.
Wow. Yeah, that's quite a find, isn't it? And such an incredible speed. Have they worked out how long it will take to exit the galaxy? Probably a long time, even at that speed.
Very, very long time, even at that speed. So we can probably try and back of the envelope mental arithmetic this. So I'll get everybody online to forgive me, but speed of light is 300,000 kilometers a second.
Yep.
I'm going to say that this is 600 kilometers a second because that just keeps the maths easier, right?
Yeah.
600 over 300,000 is 6 over 300, which is 2%, thereabouts. So this thing's traveling at 2% of the speed of light. That's fairly significant. Now, the galaxy is going to be pulling it back and slowing it down as it goes. But if you think about the diameter of the Milky Way is about 100,000 light years. So that means the radius of the Milky Way is about 50,000 light years. If you're traveling at 2% of the speed of light, that means it will take you 50 years to travel 1 light year.
Right.
Right? So 50 years per light year for 50,000 light years is 2.5 million years.
Okay.
Now, that is a long time for us, but when you compare it to the fact that it takes us some 250 million years or so to go around the middle of the galaxy, that gives you a sense of how quick this is actually moving.
Mm-hmm. Fascinating. All right. So far, the fastest found, but there may be others. We'll probably find another one that's faster at some stage. Yes, you can read about that at space.com, or if you want to read the actual paper, it was published this month in the Astronomical Journal. This is Space Nuts with Andrew Dunkley and Professor Jonti Horner.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
Now, Jonti, let's move on to this problem with dandruff in space.
Yeah.
That's what it's described as. It's not really dandruff. It's just neighbouring solar systems dumping their stuff on us.
Absolutely.
I didn't know that was a thing.
And us doing exactly the same back at them, it should have said. No, it's
Only ask.
one of those things that I talk about a lot in the context of our solar system. We have comets and asteroids, and the main way that comets get removed from the solar system to no longer pose a threat to the Earth is that many of them escape the solar system never to return. Usually flung out by one of the giant planets or by subtle gravitational perturbations like that. So you can look back over the edge of the solar system and it has continually been shedding comets and asteroids into the void of space, creating these interstellar wanderers, essentially. And that will have been particularly strongly the case, incidentally, when the solar system was still forming, because a big part of the formation of the planets and the cleanup afterwards was getting rid of most of the stuff that was left over. So the solar system over its time will have shed uncounted objects into space, and it continues to do so today. And I've often said in those talks, it's almost certain that every other star will be doing the same thing, because any star that has a planetary system, those planets will be stirring things up and throwing things out. So it's one of those things that I've just taken for granted, but it's only recently that we've actually been able to detect the products of this from other stars. Like I said, for decades, people have talked about the possibility of us finding interstellar objects in the solar system. So seeing comets or asteroids coming through that could be absolutely and definitively shown not to have an origin in our solar system. How do we do that? Well, we'll look at how quick they're moving. It's just like what we were talking about a minute ago with the escape velocity. Objects moving around the sun are gravitationally bound. If they get a nudge and they're going to escape, they will be traveling a bit too quick to be gravitationally bound, but only just by a tiny amount. So when we find an object that comes in, we can work out what speed it would travel at if it was infinitely far from the sun. Call this the velocity of infinity. So once the sun has slowed it down as much as it can, how much speed has it got left? And 2 objects that were found in the last decade met this criteria of being interstellar. They were Oumuamua, which came through in 2017, and despite what a certain eminent person at Harvard, and I'm trying to choose my words carefully here because I have a certain opinion, despite what he keeps trying to tell you to sell his books and make a lot of money, that was not an alien spaceship. It never would be an alien spaceship. It absolutely was not aliens. That was just a lump of rock and debris. We then had Comet Borisov back in 2019, which was our second interstellar object.
Yeah.
We found 2 of them. Now, the odds are that in the coming decade, we will find hundreds because the Vera Rubin Observatory is going to come online. Vera Rubin Observatory, of course, named for one of the great astronomers of the 20th century, who was a woman in astronomy, and that's a challenging thing to discuss at the moment with what's going on in the US. I will just mention in passing that is itself a controversy this week, because with the new government in the US, they've been forced to change the biography of Vera Rubin on the website because one of the things that she was very active on was advocating for women in science and, setting up schemes to try and help women get more involved in astronomy. And now you can't talk about that. Anyway, that's an aside, but it's a bit of a frustration of the human element of this.
Yeah.
The Vera Rubin Observatory, named after this incredible astronomer, is going to come online in the next year or two, and is forecast to find tens or hundreds of these objects because we'll just be much better at spotting them.
Mm.
What the new research is some computer modeling. A group has had this same idea that we're just talking about and said, let's model this. Let's try and get a handle on just how much stuff nearby star systems are throwing our way to fill the space around us. And they looked at our nearest companions, the Alpha Centauri system, which is a binary star of Alpha Centauri A and B, and then the red dwarf Proxima, which is currently a bit closer to us than the two biggest stars. They ran some simulations very much of the ilk that I do in my day job running on the supercomputing cluster here, saying if this star system has the kind of objects in it we'd expect for a system of that age, how many are getting ejected in our general direction? And what they have found is that their simulation suggests there could be as many as 1 million objects bigger than 100 meters across passing through our solar system at the current time that departed from the Alpha Centauri system. Now, the subtlety here is a lot of the time when we talk about passing through the solar system, we think of our local part of the solar system, the orbits of the planets. But in reality, the volume of space we're considering to be the solar system here is the entirety of the Oort cloud. So this is a volume of space, something like 2 light years in every direction from us. So it's an unimaginably vast sphere of space that has these objects passing through it. So the likelihood of one getting close enough for us to detect in the near future is pretty low, but it's not beyond the bounds of possibility. And again, when Vera Rubin comes online, if any of these are in, the domain of the planets, they're coming close enough to the sun that they are detectable, Vera Rubin will find them. Now, 1 million objects spread over the Oort cloud, to be honest, means that it's very unlikely one of them will be close enough to see. But these things are going to be traveling faster than the escape velocity of the sun, so they'll come through fairly quickly. And that means if they're moving through, just because we don't see them now doesn't mean if we look again in 5 years' time, there wouldn't be one that's appeared. The other thing that came out of this is that they talked about the smaller particles are more common. And it's quite likely that there may be as many as 10 meteors per year on the Earth that are bits of dust from the Alpha Centauri system hitting our planet. Now, 10 per year across the entire surface of the Earth means you're very unlikely to find them. But it reminded me of stories that go back much further, because we have these wonderful networks of cameras across the Earth that look up at shooting stars and try and get multi-station observations so you can do trigonometry and figure out what their orbit was, how they were moving. And they've detected over the years a very small number of definitively interstellar meteors. So meteors coming into the Earth's atmosphere with a speed significantly higher than 72 kilometers a second, which means that they can't have been bound to the solar system. One of the things that those papers discussed for a long time is that there is one dominant source of dust through our solar system that gives us more than all of the sources combined. A famous star called Beta Pictoris, which back in 1983 was one of 3 stars the infrared astronomical satellite was confused about because it found an infrared excess around that star. It's about 63 light years away. It's more massive than the sun and hotter, but it's very young. And it's still got a disk of debris around it forming planets. It's got planets in that disk that we've discovered. But that incredibly active stellar wind that massive star has is blowing lots of the dust into space, streaming off in all directions. And enough of that dust is traveling to reach us 63 light years away that we can detect that as a distinct source of debris crashing into the Earth's atmosphere. That really boggles my mind that a star that far away can be putting dust into our atmosphere at a sufficient level that people have detected that dust stream.
Yeah, it is. It's amazing. And this must be happening just about everywhere. We've probably got systems exchanging junk constantly.
Yeah, absolutely. And it ties into the panspermia idea that we've talked about before as well.
Yeah.
If you are constantly ejecting dust and debris from every planetary system, if you have somewhere with life in that system, eventually that life has the potential to travel. And, most of the debris ejected from the Earth will never land on any other world. It'll just float in space for forevermore. But enough has been ejected that eventually something ejected from the Earth will land on a planet around another star, or will be incorporated in a planet-forming region around a star that's just been born. You put enough material out there with enough bacteria buried in it, it's very reasonable to imagine that you could get a situation where some point in the distant future there is a planet that has life on it, and that life is having the discussion of how did life get started. And someone suggests, well, maybe life came from the stars, and everybody says, well, that's a load of rubbish, stop watching Star Trek. And after it was the case because it's Earth life.
Yes, indeed. And this story also proves that you shouldn't get upset with your neighbours for throwing the grass clippings over your fence, because it happens right through the cosmos.
Oh, absolutely. I mean, it ties into the other space Dandruff thing, actually. So this is, the whole Dandruff connection here, of course, is the stars shaking their head and comets flying through space, essentially, the beautiful analogy there. Yeah. But any time you're walking around outside, or any time you're doing the dusting in your house, a certain amount of the dust that is falling on your shoulders or that is accruing in your house is dust from outer space. We have these tiny little particles of dust, which are sometimes called Brownlee particles. They are small enough that they are slowed down by the very tenuous outer atmosphere before they get into a thick enough layer of atmosphere that they get ablated before they burn up. So there's this steady little sleet of microscopic dust particles from space raining down on the Earth all the time. So when you do the dusting, or when you go outside on a day and you're getting dust on you, a tiny fraction of that is space. So you've got space dandruff raining down on you at all times.
Yeah, it is fascinating to think about. I think we have touched on that story once before a while ago, but yeah, fascinating. I think if we're quick, we can squeeze in one more little story. If you want to chase up the space dandruff story, lifescience.com carries that one. One last yarn, and this one is something I think we touched on in the last couple of weeks about, where does a planet start and a brown dwarf begin? And we talked about 13 Jupiter masses. Well, now a new planet has popped up in a study that has sparked debate on that very issue.
Yes, so what we tend to do as humans in all walks of life is try and understand the universe. That's just a very fundamentally human thing to do. And to do that, we break things that are continua up into discrete packets, into discrete fractions. And we do this with a human lifetime. You grow up and then suddenly one magical morning you wake up and you're legally able to drive, or you're legally able to drink so long as you're not driving. You have these magical thresholds where we've said, one day you're an adult, the day before you were a child. You're not fundamentally any different across that barrier, but we're grouping like with like and keeping different things separated. That's what's happened with definitions of planets. This was all the rage, all the controversy 2 decades ago with the demotion of Pluto. It was the same thing. It was trying to group objects that are similar with each other in groups so that you can study them. And one of the great areas where this has happened is you've got planets, you've got stars, and in between them you've got these curious objects that people call brown dwarfs, which are things that are viewed as being too big and too massive to be considered a typical planet, but they're not massive enough to have hydrogen fusion and to shine and become a star. So the boundary to be a star is fairly clear-cut. If you get hydrogen fusion going, you're a star, which leads to the slightly quirky thing that white dwarfs and neutron stars are not stars. They're stellar remnants, so they're dead stars, which is a total aside. But between a planet and a star, there's this domain where you are not massive enough to burn hydrogen, but the temperature in your core will get high enough that you will temporarily be able to burn deuterium, which is heavy hydrogen. There's not much of that, so you'll get a very short period of deuterium burning, and then you'll just fizzle out and be a little glowing ember. Now, where that boundary is with a star is very clear-cut. It's a hydrogen fusion, and it's a very observable thing. But the boundary at the lower end, where you no longer have enough mass to burn deuterium, is much woollier. And if people do modelling, it depends on the composition of the object and how much solid material it's got and how much deuterium it's got and all sorts of things going on. So what's happened historically, because we didn't really have the capacity to find low-mass objects, is people just put this arbitrary boundary of 13 Jupiter masses there to say anything more massive than that is a brown dwarf, anything less massive is a planet. So that is setting this boundary purely on the physical mass. It's taking no account of the composition of the object or how it formed. And as we finally got the ability to find objects of this mass, people have started to question that. because the formation mechanism of the composition matters. A planet like Jupiter has about 30 Earth masses of solid material as a core because of the way it formed. A star doesn't have that same kind of structure. So there's a growing argument that maybe we should divide it by formation mechanism, and something that formed like a planet is a planet even if it's more massive than this limit, and it probably wouldn't undergo deuterium fusion because a lot of the mass is solid material, so it's got less deuterium. Alternatively, if it formed like a star, even if it's less massive than 13 Jupiter masses, maybe it should be considered a brown dwarf rather than a planet because of the formation mechanism. And it's a debate that's only just starting to kick off because we're only really able to find these objects now. It's been fired up here by the discovery of what's known as Gaia 4b. So the Gaia spacecraft we talked about earlier is this incredible mission that was measuring the positions and the motions of 1 billion stars with incredible precision, 2 billion stars. Absolutely ridiculous. And what Gaia has promised for a long time is that it would find 100,000 to 1 million planets around other stars. That was part of the marketing. So far, it has found 4 or 5. More will come because they're still doing their big data releases, so it will give us a deluge of planets at some point. But the reason it can do this is that it measures the positions of the stars in the sky so accurately that it can see them wobbling as they move as a result of the planets pulling them around. So this is a counterpart to our radial velocity method. Radial velocity sees a movement back and forth on a line of sight. Gaia sees the movement at right angles to that. So it's been looking at this star. This star is less massive than the sun, about 2/3 of the mass of the sun. And this star's moving across the night sky because it's moving through the galaxy separately to us. It's what we call proper motion. And Gaia's identified that instead of that proper motion being a straight line, it's following a corkscrew path across the sky, zigzagging. And that's a telltale sign it's got a planet going around it. Now, because this star's a bit like the sun, it's a bit cooler, you can do radial velocity observations, which means you can measure the line of sight wobble as well, which means you can perfectly constrain what's going around it. And the evidence here is that this is an object 11.8 times the mass of Jupiter. So it's just underneath that threshold to be a brown dwarf. We would traditionally call it a planet.
Yeah.
And job done. The complexity comes, though, that this star is less massive than the sun, and it's got a roughly similar composition to the sun. What that means is the material the planets around it would have formed from would have been similar to that around the sun. It's not particularly metal-rich, so it wouldn't have had far more solid material around it than the sun did, which means there's a really difficult question to answer, which is how can a star less massive than the sun, which presumably formed from a less massive cloud of material than the sun, how can it form a planet 12 times more massive than the biggest planet we have in our system? That just doesn't make much sense. It's really counter to our planet formation models, which is more massive stars form more massive planets. So that then brings up the suggestion that maybe this thing didn't form as a planet at all. Maybe instead what we're seeing is a failed binary star system. And this 11.8 Jupiter mass object formed in the same way that binary stars would form. That it wasn't core accretion. You didn't get a load of solid material grow to 30 times the mass of the Earth or 10 times the mass of the Earth and then start gathering gas because of the gravitational pull. That instead it formed through gravitational instability in the cloud like another star would form.
Right.
And therefore, this could be considered a failed star. In which case, it should be called a brown dwarf even though it's not massive enough because it didn't form as a planet. It may even be because it's so close to the threshold that it could have almost got to the deuterium burning limit. It could have had that happen. Now, we don't really know. If we could go there, if we could borrow Captain Kirk's spaceship and engage warp drive and go there, we'd be able to answer this after a little while. We'd put a mission up like Juno that's going around Jupiter. That would allow you to map the interior of the object, a bit like the earthquakes we were talking about in the first topic, and figure out if it had a core or not. And that would tell you about its formation. But we can't do that. We just can't get there. So at the minute, it's purely in the domain of speculation, but it's a sufficiently odd discovery that it is just restarting that old discussion about at what point do we need to look at this again, I guess. At what point do we need to discuss whether we get a more physically motivated difference between brown dwarfs and planets, or whether we're happy just sticking with this arbitrary mass limit. And as the years go on, Gaia is going to discover far more objects. We continue to find planets using all the other methods. there will be more objects that straddle that boundary because nature forms things of all sizes. It doesn't say, I'm going to leave a gap here to make it nice and easy for you. There'll be things of all masses, and there will be things of identical masses that formed in different ways. And so it's going to be an ongoing question. I'm sure we could have a chat in a couple of years' time and they'd still be having the same debates. But it's great when you get to the point where our ability to find things is such that it pushes the boundaries of how we define things and we have to revisit them. That's how science works, and I really love it, even if it means you get cranky people waving flags and going, Pluto should still be a planet.
Yes, and that's still happening too, yes, indeed.
Absolutely.
Yeah. All right. If you would like to look into Gaia 4b and 5b, they've posted a report in the Astronomical Journal. It's a fascinating discovery, and I imagine the more we look, the more unusual things we'll find. And yes, we probably will have to redefine where a brown dwarf starts and a planet finishes in the future. It might come down to that. But at the moment, we just go with what we know until proof sends us in a different direction. We are just about done. Jonti, thank you so much.
That's an absolute pleasure. Thank you for having me.
Always a pleasure. And we'll see you real soon. Professor Jonti Horner from the University of Southern Queensland. And thanks to Hugh in the studio, who couldn't be with us today. He's very embarrassed. He's got a severe case of space dandruff. Don't forget to visit us online as well at spacenutspodcast.com or spacenuts.io. And from me, Andrew Dunkley, thanks for joining us. We'll see you on the very next episode of Space Nuts. Coming soon. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.